Alright, we have started recording, and we take you to practice quiz. So today we're doing a replacement for section 9.4 in the textbook. It's not a very good section. It's kind of that topic, I have better stuff than what's in there. So that's why it's called replacement for 9.4. And the practice quiz, these are some things that we didn't get to last time in class. So number one, solve and interpret your answer. There's a differential equation with an initial condition. There's a situation, what things represent. So solve this differential equation with this initial condition. It's called an initial value problem. And very important though, when you're done, interpret your answer. So a solution of a differential equation is a function y. I'll give you a little bit of time on this. And let me give you another minute. Okay, so when we have this differential equation, we can solve it by separation of variables if we want. Do dy dt, get the y on one side, the t on the other side. But when there's no plus anything else, we can also do this the fastest way possible. We can say, what is the function whose derivative is this constant times itself? And that function is, the solution is y equals e to the negative 0.01 t. Because if I take the derivative of, I get itself, times an extra negative 0.01. And then it can have any constant out front, c. Plus c doesn't work, but times c does work. And then we can look at this, y of 0 is equal to 20, plug in 20 here, plug in the 0 for the t, and then that'll tell us that 20, e to the 0 is 1, 20 is c. So then the solution is y equals 20 e to the negative 0.01 t. That's the function that gives us this when you give an initial dose of 20 milligrams and it dissipates or gets absorbed by the body 1% every hour. You get this function. Now, we should get familiar also with, when you're interpreting this, it's helpful to see it. If this was 10, this is 20. So this is the time t. This is the amount of drug in the bloodstream. And when t is 0, this is going to start at 20. So it's going to start here. And as time goes on, it keeps getting less and less and less. This should either come down to the t-axis like this, in a concave down manner, or it should come down like this, in a concave up manner. So, which way should it come? Down to the t-axis. And does anybody have an instinct about that? Should it come concave down, the solid green line, or the dotted green line, in a concave up? I'll open it the floor to anybody. Anybody have an instinct there?
This is Rowan. My instinct is that it should concave up.
The dotted.
The dotted line.
And
Yeah.
can you explain why?
I just, because I know that e, like the function of e to the t, kind of concaves up, but it goes the other way. So I think that if we've just got like a negative value, it just concaves down.
Very nice, very nice. And also, when you lose 1% every hour, the first hour, you're going to lose 1% of 20, which is, now 10% would be 2, so 1% would be 0.2. You're going to lose 0.2 milligrams. But when this gets down to, let's say, 10 milligrams, then in that, once it has hit down to 10 milligrams, the next hour it's only going to lose 0.1. So it's losing the most right at the beginning. And the further you go down, 1% of smaller numbers is smaller values. So it's actually like this. And its asymptote will be the t-axis. But just as Rowan was saying, we get it concave up like this. All right, and the picture makes sense. You get 20 milligrams in your bloodstream and you get this. Now, when you lose, and this is kind of just in general for exponential functions, when you lose a certain percentage every time period, you could think of it in a way like there's some portion of the drug that's always going to stay in your body. Because, you know, if it was infinitely divisible, it turns out it's not infinitely divisible, but, you know, kind of theoretically, if you take 1%, which is, you know, just 1/100th of what's there, there'd still always be something there. When you take a drug, yes, it's being absorbed at a faster rate right at the beginning than as time goes on, less and less going into your bloodstream, out of your bloodstream. All right, let's go to number 2. Oh, before this, give me some feedback on this. Use the same protocol. It was over here from last time. Just rate the review as a review activity. 1, 2, and 3, and give me just a few words at least in feedback. And go ahead and hit enter. Okay. Let's go. I like this material as well. When I see the applications of this, it gets me very excited. All right, number 2. solve and interpret. You're hearing somebody? You might have to mute your microphone unless you're wanting to talk. Thanks. All right, number 2, similar kind of problem, but it's a little more complicated equation, and the plus 4 has a special interpretation. The drug is being intravenously added at 4 milligrams per hour. That's what the plus 4 in, see, because remember, dy dx, y prime. The interpretation of that is the change in the output, so the change in milligrams of drugs, every time the input increases by 1. So how much the milligrams of drugs is changing every time an hour goes by, provided we stay in the tangent line. Now, 2 things are happening. In one sense, drug is going into the system, you're adding it. In the other sense, drug is coming out of the bloodstream because your body is absorbing it at 1% of it per hour. So those 2 contradictory things, one is negative, one is positive, that's their contribution into the y prime. And, all right, so go ahead and solve and interpret your answer. So notice when we interpreted this one, we drew a picture of it. A picture might be good as well for your interpretation. Excuse me. So this one takes a little more time. I'll give you a bit more time yet. 30 seconds more. Alright, because of this plus 4 up here, we cannot use this shortcut. Now, if it didn't have the plus 4, the answer would be like before, y equals e to the negative 0.01t. That's going to still show up, because that's an integral part of the relationship between y and t right here. But this plus 4 really does a number on that. It's going to make it quite a bit different. So the only way we know how to solve this is separation of variables. So I'm going to multiply both sides by dt. I'm going to divide both sides by what's on the right, negative 0.01y plus 4. Now I've separated. All the y's on the left, all the t's on the right. So now I am able to integrate both sides. And on the left side, I'm going to get the natural log, the absolute value of this stuff. Now if I took the derivative of this, I'd get an extra negative 0.01 showing up, so I have to divide that out. And then on this side I'd get t, and I've removed all of the integral signs, so plus c has to occur on at least one side. Since I'm solving this thing for y, that's why I put my plus c on the other side. I could have put it on either side. Alright, so then I can find out what that c is at any point. I could plug it in right now and find out what that c is. In fact, I vary it. Sometimes I do it right away, sometimes not. So let's go ahead and just plug it in now. When the t is 0, the y is 20. Now, this is going to be what? Negative 100. When you reciprocate 1/100th, you get 100. ln, and then 20 times 0.01 is 0.2, so it's negative 0.2 plus 4 equals 0 plus c. So this is c is equal to negative 100 natural log of 3.8. So we found the c right there. It might be easier to ignore what I just did and wait until later to find the c, because we're going to be doing, but let's just go with it this time, see what happens. So I have my problem right here. I got to get y isolated. So first thing is I got to get rid of this constant. So I multiply both sides by negative 0.01. And these cancel out, and I'm going to be left with ln this equals the negative 0.01 multiplies into the t. The negative 0.01 also multiplies into the c, but the c was this over here. And so it's going to be negative times negative, that makes positive. The 0.01 times 100 kill each other off. 1/100th times 100 is 1, plus ln of 3.8. Alright, and then I'm going to get the y all by itself. I'm going to put a giant E underneath both sides so that these cancel out. And I'm going to get this. It's the absolute value. Now this is going to be times, because remember, when the bases are the same, you just add the exponents. Now here you see, when we found the c kind of early, you gotta manipulate these things, so it might be a little bit more work this way. But this just turns out to be a normal 3.8. The e and the ln kill each other off. And this is always positive, because e to some power is always positive, and that's why there's this absolute value here. But in reality, we can drop the absolute value. Once we realize why that absolute value is there. And then we subtract 4 from both sides. Divide both sides by negative 1/100th. I'll divide every term by that. And then I'm going to get y equals negative, now this is the same as multiplying by 100, so move the decimal 2 places to the right. 380 e to the negative 0.01 t. And then plus, move the decimal 2 places to the right, 400. Alright. Now, what I see about this is, if I was to make a graph, when t is 0, e to the 0 is 1. 1 times negative 380 is negative 380, so I'm going to get 20. This original thing starts at 20. And then, you might see it a little bit clearer if I rearrange this. Look at that solution this way. And if we do it like this, we might want to go like this, because we need to go all the way up to 400. And 20 is way down here. And this thing is going to start at 20. Because when y, that's its initial condition. Y of 0 is 20. Right here. It's going to, as t gets larger and larger, this thing will get larger and larger. When t is 0, that's 1. When t is 1, this is a little bit more than 1. About 1.01. As t gets larger and larger, this gets larger and larger, and it drives this whole fraction that's being subtracted, drives it smaller and smaller. What does that mean for the entire function? it means we're going to wind up increasing until we get close to that, and then get infinitely close. We'll get really, really close to 400 milligrams. And it makes sense in this other sense as well. You keep losing only 1%. Imagine what happens in the very first hour. T, Y, approximately. So just approximate. When T is 0, you start with 20 milligrams. When T is 1, you had your 20 milligrams that you started with. You lose 1%. And you gain 4. See what's going on here? You're gaining a lot more than you're losing. Alright, and so you're going to be close to 24 after the first hour. And you're going to keep gaining and gaining until you get really close to 400. Why is 400 the magic number? Because what is 1% of 400? 1% of 400 is 4. When you finally get up to around 400, then the 1% loss is balancing out with the 4 gain each hour. And so that's why this graph is going to have this horizontal asymptote at 400. Give me a comment on this. You might also comment on this one about if this is making sense or you kind of got lost, and about the review here. Go ahead and type that in. Don't hit enter quite yet. And go ahead and hit enter. Yeah, I did start the recording. Thanks for checking. Okay. This looks like we might want to repeat some of this stuff again. Not everybody's following all the parts. Yeah, it is kind of complex. That one little extra thing, this +4, really changed. Let's contrast. Look at how simple the solution was over here. But when you're adding, you put this little +4, you're adding. Now what that really means is this is an instantaneous rate of change. So that IV is coming out in an instantaneous rate, so that over the course of an hour, 4 milligrams would come in. And but this e to the negative 0.01 t does show up again over here, but it has these coefficients and this sum that makes it really makes sense. And one thing I want to do, because it's so important, is why 400 was so big. You're losing 1% per hour. You're going to be losing more than you're gaining. I mean, you're gaining more than you're losing when you first start. 1% of 20 is 0.2. But when you get up to 400, 1% of 400 is 4, so then your loss and your gain each hour would finally balance out, and that's why we get really, really close to that. Alright, we have a test coming up a week from today. It covers a lot of material. One thing that it covers is Chapter 8, which is um, all those integration techniques. Name the different methods of integration and how you can tell when to use that method. So, from memory, don't look these up. What are the different ways that we learned how to integrate? And what would be a clue that would tell you, I need to use this? Okay, let me have you stop. Go to your group chat and start typing in. Everybody type in one or two methods of integration, and then look at the others until you think you've got a complete list. And you might throw in some ideas about how you can tell when to use one of those. And you can start hitting enter right away. All right. Let me get a little countdown with the groups. So if everybody could, if you haven't already typed in something today, type in hi in your group. So that, and group leader, make sure the spokesman for the day knows who they are. And let me just check how many people are in each of the groups. Group 1, how many of you are here today? How about group 2? How many are here?
There are two of us.
Group 3?
There are 4 of us.
Group 4?
One
Just one of
of
One.
yeah.
Okay. Group 5? Nobody in group 5?
Not too sure.
One of you maybe? Okay.
Maybe I'm not sure. Nobody else said anything.
Okay. Looks like just one then. And then 6? Group 6, how many of you?
There's 2 of us.
And group 7?
There's either 3 or 4.
Okay. And, alright, so I'm going to have group 5, you join group 6. So unmute your channel for group 6 and immediately go in there and say hi, so they know who you are and that you're part of that group. And group 4, you join group 2. Do the same for group 2. And if there's anybody in group 1, you also join group 2. Alright. And let me ask group 7, what do you have for different methods of integration? And how can you tell when to use a method?
Well, the ones I started with, I'm not sure if this is all of them or not, but I had like just direct integration, like if you just had like x cubed plus x squared or
Okay,
something
there's a name for that, and that's power rule.
like that.
Power rule for integration. Okay. Is this Matthew?
Yes.
Okay, you got any more?
Then I had like trig integration, like with the identities.
Okay. What else?
With like a u substitution.
Very good.
By partial fractions.
Okay, partial fraction decomposition.
And then the one we did last class, which I forget the name of. What was the name of the one we did last class with like x and y?
Separable?
Yeah, separable.
Okay. Now that's in the context of solving a differential equation.
Yeah.
It is another method of integration. We integrate, but I'm not going to put it in this list though, because I'm kind of focusing on the chapter 8 kind of concepts right now for this. But I'm glad you brought that up. Okay? And can anybody think of another?
Improper integrals.
Improper integrals. Anything else? There's one more big one. Nobody remembering it?
Is it the back of the book stuff?
Back of the book. Yeah, but I'm not going to put that in there. Integration by parts. What is integration by parts? What's the formula for that? Anybody?
It's the integral of u dv equals uv minus the integral of v du.
Very good. You got to have a formula memorized to do this one. All right. Let me just give a few words about each one of these. The improper integrals. You might not detect it as an improper integral right away, because you might be like either the left endpoint, the right endpoint, or you might come right across it in the middle. There might be a vertical asymptote that you're integrating across. And so it might look like a normal looking integral. The ones that are easy to identify is if it has infinity on the bounds, it's integral from 0 to infinity or something like that. And all of these, you must turn it. It must become a limit. If you're able to do it without turning it into a limit, I still won't give you complete credit because that's how it's defined. Okay. So identifying something that's an improper integral can be kind of tricky. And we kind of have to learn to get like a new awareness that, if I see something in a variable in the denominator, then if that denominator can never become 0, then I can be having an improper integral. Integration by parts, what might clue me off that I need that, is when there's two things that could be integrated separately, but now they're being multiplied together. Like e to the x times x, or something like this. But we even used it to generate the rule for ln x, the integral of ln x, even though that wasn't two different functions. We solved that one by integration by parts. So it can be kind of tricky of deciding which one am I going to use in which situation. When you were doing the individual sections, you knew what to do, but on a test, that's a big complicating factor. You don't know which one you're going to use, so think about that as you're getting ready for the exam. All right, partial fraction decomposition. We do that when we had integrals of a polynomial divided by a polynomial. U substitution. U substitution goes through all of these things. Many of them need a U substitution before you can do any of these. And the trig functions are kind of, it's pretty obvious when it's trig, but you got to have a bunch of memorized things. You have to know, the derivative of tangent is secant squared. You got to have the Pythagorean identities memorized. Secant squared, well, the more complicated one, tangent squared plus 1 is secant squared. Review the memorization of those things as well. Okay. All right. And let me insert a little bit. All right. I am going to go right into 9.4, this replacement for 9.4. We'll hold off on questions until later today because I want to make sure I finish this stuff. And last time we kind of left some of that stuff undone, but we got to that in the practice quiz today. Alright, so this is some of my favorite stuff in all of Calculus 2. And as I mentioned before, typical class, if you're like an engineering major, basically almost any type of engineering, a very typical class after taking the calculus sequence is take differential equations class. And this is a kind of a problem that you'll see early. It's a very typical kind of problem in a differential equations class. And if your experience in a differential equation class is anything like mine was, it was kind of light speed. It was like, here was a problem like this, it was put up, and then in 5 minutes we had a solution. And I couldn't understand anything while the instructor was doing the problem. I could just take notes, and then later I had to pore over it for hours to figure out what went on. And so we'll take our time with this, and I'll break it up into lots of stages, and I'll have questions along the way. All right, so the application is concentration of salt. And when you mix salt and water together, we call that brine. A tank initially contains 200 gallons of brine with 500 pounds of salt in the solution. So, question number 1, what is the concentration of salt? And give the units. And let me give you a brief bit of time to figure that out. Okay, and type that into your group chat. Go ahead and type that in right away. So group 2, what is the concentration of salt?
We're not too sure yet.
Okay. Let me try, and that's fine. Group 3, what's the concentration of salt?
We're saying 25.
What would the units be?
0.25 pounds per gallon.
0.25 pounds per gallon.
But I feel like that's supposed to be 25%.
Ah, well, let's look at it in terms of percent as well. Okay, so it looks like what you did is you took 50 pounds into 200 gallons, reduce the fraction or punch out in your calculator, and that's the same as 1/4 or 0.25. 0.25 pounds per gallon. Now, would we want to call that 25%? I think in this case, we'll just leave it as 0.25 pounds per gallon. The reason why I wouldn't necessarily turn it into a percent is because if I had a liquid and a liquid that I was comparing, then I could be doing volumes. 25% of the volume is this other thing. But since we've got a solid and a liquid, it's not really 25% of the weight, it's not really 25% of the volume, it's just 0.25, 1/4 of a pound of salt in every gallon of brine. This is what this means. All right, any questions on number 1? Pretty clear on that? All right, so that's its concentration. We're going to assume that it's well mixed. All right, now, the next portion. Brine containing 2 pounds of salt per gallon is entering at a rate of 4 gallons per minute and is flowing out at the same rate. So we might think of this as, we've got this great big barrel. That's holding 200 gallons. And we've got a hose dumping brine in, and then we have a little spigot at the bottom where it's coming out. So it's coming in at 4 gallons per minute, it's coming out at 4 gallons per minute. If the mixture in the tank is kept uniform by constant stirring, so it's stirred up constantly, find the amount of salt in the tank at the end of 40 minutes. That's what we're going to eventually get to, but we're going to get there by stages. Now, it turns out, this is one of the problems, there's a theme of this in math in general. We're asked a very specific thing. What's the amount of salt in the tank at the end of 40 minutes? I know I started out with 50 pounds of salt. At the end of 40 minutes, I'm going to have a different number of pounds of salt. I'm asked for a specific number. It turns out that that question is too hard to answer if we think of it only as one finite question. The question actually becomes much easier to answer if we say, what is the amount of salt at all time in it? And we're going to be able to solve that problem. And so when you make the problem bigger, and it makes it way bigger, what is the pounds of salt at every moment of time? Well, that one we can solve. And then we can go back and solve this particular problem. All right, so question number 2, though. Is the tank getting more or less salty as time goes on? So think about that for a moment before you type anything into your group chat. You can type it up, but don't hit enter. So you might be typing up, what you think your possible answer is and why. Okay, go ahead and hit enter and any possible guess and why into your group chat and discuss it briefly. I'll call on a group in a minute. All right, let me call in group 6. Is it getting more or less salty? Anybody in group 6? You can always pass. All right, let's go to group 7. Is tank getting more or less salty?
I think that the tank's getting more salty because the salt water that's getting put in is a higher concentration than what's coming out.
It's what's going in is its concentration of what's coming out initially is 0.25 pounds per gallon, but what's going in initially is how much? It says it's 2 pounds of salt per gallon. And that's 1/4 of 1 pound, and that's 8 times as big. So it's a lot more concentrated salt coming in than what's going out. Seems to make sense. Yeah. Okay, now number 3. The input variable will be t. The output variable will be y. Describe each with a complete sentence. T and y. And that makes sense for how you would describe your variables to answer the question and eventually find the amount of salt in the tank at the end of 40 minutes. So for both of those, again, you might type in your answers into group chat, but don't hit enter yet. So work individually first. Go ahead and hit enter. Check out other answers. Group 3, what do you have for time? I mean for t.
Hold on. Well, I thought T was salt and Y was brine, or the solution.
Okay?
Someone else said T is a constant at which salt is added to the system. I don't know if that means the same thing.
Okay? So that gets us going. We have some ideas about the input variable and the output variable. All right, and a general rule of thumb is, because they talk about, like, if you look at the thing that's being asked of you, usually you can find your variables in there. Find the amount of salt in the tank at the end of 40 minutes. So,
Oh, so T is time and Y is salt.
very good. Let's T is time in what units?
In minutes.
Time in minutes. And Y is, what did you say Y was?
Salt,
Now, there's
which
different
is
ways.
pounds per gallon.
Now, do you want concentration of salt, pounds per gallon? Or do you just want the pounds of salt?
I think we want just pounds of salt because it's saying 4 gallons per minute, which is a rate, which means that that is the slope of change between T and Y.
Right. That is very good. A lot of students want to try to make pounds per gallon or something like this here, but we can do that later with our own stuff. We want to make these things as simple as we possibly can. Pounds of salt where? In the tank. The total pounds of salt in the entire tank. Now, when we have our variables set up like this, we're ready to go and to do more, but it is break time right now, so we will start again. At 6:45 p.m. And does anybody need to talk to me individually before I take my break? All right, see you in a bit. job to do. Come in. I'm starting right now. All right, we are starting again. And we've got our variables, and we have these three questions. At what rate is salt entering the tank? What are the initial conditions? Like you're going to set up a differential equation, and the initial conditions, write an equation for that. And then at what rate is salt leaving the tank? Be as specific as possible. So for 4, 5, and 6, we give you a little bit of time, and you can enter your answers into your group chat. But work on it individually first. I'll tell you when to hit enter. Okay, you can hit enter. Discuss any of these with your group. Okay, group 7. At what rate is salt entering the tank?
I said 8 pounds per minute.
How'd you get that?
So it says that the water enters at 4 gallons a minute and that there's 2 pounds of salt per gallon. So just 4 times 2.
Ah, so 2 pounds per gallon. This is what we call the concentration. Of salt. But it's entering at a rate of 4 gallons per minute. That's the rate at which it's entering. Oops. The rate, but not of salt. It's the rate, come on, of the brine that's coming in. Now, if you multiply these two together, 2 times the 4 makes 8. The gallons and gallons cancel out, and you get pounds per minute. And this is the rate of salt. It's 8 pounds of salt. Rate of salt entering. So let me 2 pounds per gallon times 4 gallons per minute equals 8 pounds per minute. Okay, same group. What are the initial conditions?
I thought that it was 50 pounds of salt since it said that the tank initially contained 200 gallons of brine with 50 pounds of salt in the solution.
Okay, you're right on track. But give me initial conditions, something for both variables. Something for t and something for y.
Oh, it's like when time is 0 minutes, there's 50 pounds of salt.
When t equals 0, y equals 50. That's the idea. It's usually not stated this way, though. Usually it's stated like this. Y of 0 is equal to 50. Y is a function of time depending on time, and then we have that. That's the initial condition. That's what we started with. All right. Let's go to number 6. At what rate is salt leaving the tank? Same group.
I wasn't really sure about that one because, like, well, originally there was a quarter of a pound of salt per gallon and it exits at 4 pounds per gallon. But then it seemed like as you added water, the concentration would go up, and so like the amount of salt leaving would constantly be changing.
Very good. It varies. Initially, it leaves the tank at what rate?
1 pound per minute.
How'd you get the 1?
Since originally we decided that the concentration was 0.25 pounds per gallon, and then the water also exits at 4 gallons a minute.
So this is going to happen 4 times every minute. So we cross these out and we get 1 pound per minute. Initially it leaves the tank at 0.25 pounds per gallon times 4 gallons per minute, which equals 1 pound per gallon. No, per minute. But this gets larger because the salt, we had decided it's getting more and more salty. This gets larger. Okay, number 7. Approximate y when t is 1 million minutes. So, I'm going to give you a minute for that. Type in your answer into your group chat, but don't hit enter yet. Work on it individually first. Go ahead and hit enter. Discuss this briefly. Okay, group 2, any ideas here?
We said y prime equals 0.25 y plus 8.
Y prime is equal to 0.25 y plus 8. For the differential equation? Alright, we'll get back to that a little later. That could be very interesting. That's your guess at what the differential equation is. That's really neat. But we can also just look at this by itself. Approximate y when t is 1 million minutes. Now, there's nothing special about 1 million. It's just that it's really, really, really huge. And after a really, really, really long time, is the concentration of salt in the tank still going to be what it started at about 0.25? Or, well, we had decided it was getting more salty. Does it get infinitely salty, or does it top out at something? And so can we approximate this with an actual number? And I'm going to open up the floor. Anybody have an idea for this?
I said 400 pounds because I figured by then the concentration of the tank would match that of the water coming in, because eventually all of it would get replaced.
Okay, so there's 200 gallons in the whole tank. And the water coming in is 2 pounds per gallon. The water coming out is 0.25, 1/4 of a pound per gallon. Given enough time, that initial concentration is going to be, it won't matter. It's all going to become 2 pounds per gallon eventually. So after a really, really long time, like a million minutes, it's going to be 2 pounds per gallon. And then these units cancel out. We get 400 pounds of salt. T is going to be approximately that after a super long time. All right. Then, number 8, using limits. Write an expression which describes the tendency of the function y of t as time gets very large. So I'm going to give you a minute with that. And again, you'll be entering your answer into your group chat, but I'll give you a moment before you hit enter. Okay, go ahead and hit enter into your group chat. All right, so group 3, what do you have for this?
I think that you could maybe say it's the limit as t goes to infinity of 400 plus almost any fraction where t is on the bottom in the denominator.
So the limit as t goes to infinity of, you said 400
400
plus something over t?
over, yeah. Or I suppose you could also maybe use e to the t.
Okay,
Yeah.
all right. So that as t goes to infinity, you're going to be getting something that gets really, really close to 400. I see the approach you're using. Okay. Now, the one thing about this approach, though, is this would be larger than 400, and it would be coming down to 400 because it's plus. So we might want to change that to minus. So then, as this gets smaller and smaller, we get closer and closer to 400. So we can get it like that. We can also generalize this. The limit as t approaches infinity of simply y sub t. Because y is the pounds of salt in the tank. This is equal to 400. Now this y sub t might well turn out to be something like this, like what you're pointing out, so that when we take this t goes in, so this, I like your contribution here. This could well be, might turn out to be it. For right now though, we're not sure. So let me just, for the sake of people's notes, I'm going to cross this out to say that this is what we want to focus on. But this is a contribution that we may be coming back to see that, oh yeah, this was really right. Okay. That's good thinking. Now, let's draw a rough sketch of the function y of t. And let's do this together here. We're going to t and y. And what did we say? The initial condition was y of 0 is equal to 50. And as time goes on, it gets more and more salty, and it goes towards 400. So, if we had 100, 200, 300, 400. We would start at 50. We're going to be adding salt. But as we get close to this, it's going to get really infinitely close to that without ever touching it. All right. Now, give me a little feedback at your comfort level with all this stuff. I'm very comfortable with this. Oh, it's too theoretical for me. There's certain parts that are losing me, and you might say something about that. But everybody give me a little bit of feedback where you're at with all this that's going on. And you can go ahead and hit enter when you're ready. And some of you might be like me when I was first presented with this stuff, was I was just scrambling and taking notes and didn't understand a thing until later, and hours and hours. All right. All right, so since y0 is equal to 50, we're going to estimate, we'll do this together, estimate y sub 1. Now, y sub 1 is going to be approximately 50. So, whenever we project out into the future on something, we know at time 0, and we're just starting our stopwatch, we know it's 50 gallons of salt in it, or 50 pounds of salt. Y sub 1, the best estimate for what's going to be 1 minute later is, well, it's going to be the same, unless you know something about the derivative. How is it changing? And if you know something about how it's changing, what's the derivative at time 0? Now, what does this mean? Y prime of 0 is the change in y when t increases by 1. So, y prime of 0, whatever it is, we're going to multiply that by 1, because this is just 1 minute later. If it was 2, we would multiply it by 2. If it was 0.5, we'd multiply it by 0.5. So, all right. Now, the change in y, delta means change in. Change in y in the first minute is equal to, we'll call it salt in, the amount of salt that came in, subtract salt out, the amount of salt that went out. Now, how much salt came in the first minute? Well, it was coming in at 2 pounds per gallon, and in the first minute, 8 gallons came in. So multiply those together, it's 8 pounds of salt came in the first minute. How much salt went out in the first minute? Now this is, we'll put a squiggly above this, approximately, because it's changing instantaneously. Alright, so it's not going to be exactly 8, because, these two concentrations get mixed up. But this is a reasonable approximation. Okay. And then in that first minute, how much salt went out? Well, it was 1/4 of a pound per gallon times 4 gallons, which was 1 pound in that first minute. So it's 7 pounds. So, thus, y sub 1 is approximately 57 pounds of salt. After 1 minute, you're going to have about 57. Because you had, in that first minute, 8 pounds of salt entering in those 4 gallons of brine, and 1 pound of salt exiting in those 4 gallons that came out at the bottom, and you had a net gain of 7. So then we're going to use this, the change in y, because the derivative is really the change in y when the input increases by 1. So the change in y is salt in minus salt out. Using that, we're going to create the modeling differential equation. Alright, so when we do this, we're going to get dy dt equals, now the salt in, how much salt was coming in each minute? Does that stay constant, or does it, hang on a second, I gotta let my dog out. Alright, so the salt in, is that staying constant all the time? And the salt out, is that staying constant each minute, or does that vary according to the minutes? Well, we had addressed those way back. At what rate is salt entering the tank? Well, it's coming in through this hose, and that always has this concentration. So the salt is always coming in at 8 pounds per minute. So this does not change. Salt in is going to be 8. Now, I'm not going to write the units in there because it'll kind of, but we'll just put a little arrow to this. This is in pounds per minute. Okay. Now minus, now the salt out. Salt out was the complicated one. At what rate is salt leaving the tank? It varied. Initially, it leaves the tank at 1 pound per minute. But this gets larger and larger. Eventually, it's going to become really close to 8 pounds per minute, because that's going to be the concentration. You know, eventually it's going to be all 4 pounds per minute and 4 gallons per minute leaving, as well as coming in. So this part is going to be complicated. Now, what it's going to be, though, is a fraction with units. I'm going to put a fraction bar, and I'm going to put this whole thing, pounds per gallon, times another fraction, gallons per minute. So now we can see that the gallons would cancel out, and we'd get pounds per minute, just like this 8. 8 pounds per minute here, and so this, same thing. Hang on just a minute here. Hey, John, I can hear you really clearly.
I'm going to stop.
Thank you. All right, so at what gallons per minute is the brine leaving the tank? 4 gallons every 1 minute. What is the concentration in pounds per gallon of the stuff that is leaving the tank? This is the trickiest part of the whole setup right here. And this, we said, well, it varies. It initially leaves the tank at 1 pound per minute and so on. So how in the world am I going to get this? But this can be done in a logical fashion if we remember the tank is well stirred. How many gallons are in the entire tank? So that's the secret of getting this whole thing, is you ask this question, for the entire tank. Alright, so when we think about the entire tank, there are how many gallons in the whole tank? Tells us 200 gallons in the entire tank. Since it's well stirred, if I have the number of pounds of salt at any time t divided by total number of gallons, that's its concentration. So how many pounds of salt is in there at any time t? And my first instinct is to say, well, it's constantly changing. There's no way that we can know. But then I realize that's what we set up as this variable. The pounds of the salt in the tank at any time t is y. That's what goes right there. And then we simplify this to dy dt. 8 minus, now we look at the units, pounds or gallons both cancel out. You're also getting pounds per minute over here. The 4 and the 4 in the 200 reduces to 1/50th. And that's going to be the differential equation that's going to model the situation. So, at one point I told you in this class that when you saw college algebra type problems, like, one train leaves Los Angeles heading east, and another train leaves Florida heading west, and they're different miles per hour, and when do they meet, and those are kind of equations that we can solve with college algebra, and they seem kind of contrived. And they are kind of contrived because we don't have that many tools. Real life situations that have any complexity to them lead to more difficult equations called differential equations. And these are much more complex to set up. But they're incredibly satisfying when you spend the time to really understand how these come about. Alright. So this is the differential equation. Now, think about this for a moment in a big picture sense. This is saying, how is the pounds of salt changing every time a minute goes by? Well, there's always 8 pounds of salt coming in every single minute. But we have to take into account the pounds of salt that are leaving every minute. And it turns out that the ratio of y over 50, or 4y over 200, is the concentration at any time t. So that's the differential equation. Now, we put that together with the solve this initial value problem. Remember, the initial condition was y0 equals 50. Together, it's an initial value problem. And after we do this, when we solve it, we'll have the solution at all values of time, and then we'll go to find y sub 40. So the next step then is to solve this differential equation. We've solved these kind of differential equations. This kind was in the practice quiz today. So what am I going to do? I'm going to multiply both sides by dt, and I'll get to dy equals 8 minus, now 1 over 100 is 0.01. If you multiply that by 2, it's 0.02. 0.02y. So 1/50 is 0.02, and then this is times dt. Divide both sides by what's in parentheses. So it's separable, we've separated them. It's the only way we know how to solve this complicated of a differential equation. Separation of variables, and then we integrate both sides. And the left side, this is going to be the ln of the absolute value of 8 minus 0.02y. Now if I took the derivative of that, I would get 1 over that times an extra negative 0.02. So I have to cancel that out. this is t, and then once I got rid of all the integrals, I have to throw in a plus c. This time, we are going to wait and get the c in a little while. I'm going to multiply both sides. By negative 0.02. These cancel, I get ln of this. Arbitrary constant times negative 0.02 is still an arbitrary constant, so I'll just still call it plus c. Then I'll take a giant E, and then these cancel out, and I get this. I get e to this times e to the c. Because base are the same, you'd add the exponents. So I just did the reverse of that process. And then e to the c is an arbitrary positive constant, so that's why that this had to have the absolute value. And so then once we realize that, we can replace this with any constant and get rid of the absolute value at the same time. Okay. Now it's, at any point we can determine what the c is. And I might plug it in now. Y of 0 equals 50. So if I plug in 50 here and the 0 here, I'll get 8 minus 50 times 0.02 equals c times e to the 0 is 1. Now, 0.02 is the same as 1/50th, so these two multiply to be 1. So I get c is equal to 7. And then this tells me that 8 minus 0.02y equals 7 e to the negative 0.02t. And then I gotta get the y all by itself. Subtract 8. Divide by negative 0.02. And I'm going to get y equals. Now, that's the same as 1/50th. So 7 times 50 is 350. Negative by negative is positive. 50 times 8 is 400. I can leave my answer like this. I might like to see my answer in this form though. Okay. When t is 0, this is going to be 1 e to the power. And so I'm going to get, it's easy to see, when t is 0, 400 minus 350 is 50. And that's the initial condition of at time 0 there's 50 pounds of salt. And as t gets larger and larger, this fraction gets bigger and bigger, driving this whole thing to 0. The denominator gets bigger and bigger, driving the whole fraction to 0, and this will go to 400. But we had already written that. The limit as t goes to infinity of y of t was 400. So this is making sense. And once we have this, we've solved the bigger problem. What is the amount of salt at all time? It's right here. Now we can answer how much salt at 40 minutes. And we just put in $40, and then when we punch that out on a calculator, we get 242.7, approximately that many pounds. And by the way, just for curiosity's sake, I might say y sub 1. Because remember, we had approximated y sub 1. Estimate y sub 1, and we said it was about 57. Well, let's come back down and plug in 1 into this function here for y and find out how close we were. And if I punch that up on my calculator, I get 56.93, which is really close to 57. So my approximation was quite valid. And that solves that problem. All right. Any questions? Any particular steps anybody wants to look at in detail?
Yes, I have a question. I know my first step is already wrong, but I don't know why it's wrong. I put 4 in, it's 8. And then 4 out, I was doing 50 plus 80. And then divide by 200 times 4.
All right. Your voice is choppy, so I can't really...
Sorry, how about right now? Is it more clear right now?
A little better. Try again.
Okay. I don't know why it's my speaker. So my first step, I put 4 out as plus 8 and then divide by
Your voice is coming in really poorly. I can't make it out.
Let me type.
Yeah, why don't you type it into the general chat, and then I'll look at it from there. And while Yoon is doing that, anybody else have any other questions related to this? We know the graph is going to be like this. I always found this tremendously fascinating. Why how this process gets to this. Now look at this. Way back at number 8, somebody had anticipated the answer was going to be something like 400 minus something over t, so that we'd get the 400. And that's what we got. 400 minus something over an exponential function with t. So this was great anticipation way back over here, that the answer was going to be something like that. And there was also something else. Somebody had guessed, oh yeah, this y prime, that differential equation was going to be 0.25y plus 8. And let's look at that. The modeling differential equation. Where is that? Oh yeah. Really close. We had the 8 right here, but instead of plus 0.25y, it was minus 1/50th y. But this guess at the differential equation was kind of moving in the right track. Let me cross that out for, people look back at this in the future, they realize that that's should not be the focus there. But that was kind of moving us again in the right direction over here. So some nice anticipation of what was to come. All right, let me look at what Yoon wrote. Salt out. That's 50 minus 8t over 200 times 4. So I'm not sure, Yoon, why you'd have this 4 down in the bottom. Where's the plus instead of the minus? And 50 minus 8t. So salt out turned out to be 50 plus 8t over 200. All right. I'm not sure where your 50 plus 8t was coming from. I bet you had a good rationale with that. I can't think of it. Original was 50, and then 8 is coming in every. Okay. All right. The salt out. All right, I think I'm kind of seeing 8 pounds is coming in every minute. But how does that affect the amount of salt that's going out? We want, all right, let me do this. Let me snip this. And let's take it back over here. So, and this is what you were writing for the salt out. Alright. It's too complicated to get the salt out in terms of the time, because what we want for the salt out is we're going to use this bigger idea of, for the whole tank, how many gallons are there in the entire tank at any time, T, and then what's the pounds of salt in the entire tank. Since it's well mixed, that's the rate. You'll get pounds per gallon, and then we'll have that many pounds per gallon times how many gallons, 4 gallons that are moving out every minute. And so this one just turns out to be Y, and this is 200. And then we times it by 4 gallons per minute. Now, if you try to get, well, how many pounds are in the entire tank at any time? Well, there was 8 going in at so much, but then how much was going out? Well, that was variable. It's too hard in terms of T. So you got to abandon trying to get it in terms of T and just say, oh, that's what the variable Y was set up for. Y was the pounds of salt in the entire tank. And so it would be nice if we could get it to T. And that would be a simpler differential equation where you only have the input letter on the right-hand side. But it turns out you have to use the output letter. It's too complicated to get it in one of these other ways. I hope that helps you. And any other questions? All right, now let me explain the assignment. If we go into the modules, so let me back up a moment here. Modules. Also, I need to explain something too. There's a limit in Canvas about how many assignments an instructor can set up. And when I was setting up this course, I wound up at about the halfway point in the course. I hit my limit. If I kept doing spot checks, I would go over the limit. So what's going to happen is there's going to be no more spot checks for assignments. And so you're going to see, there was a spot check for 9.3 and 9.4, there's no spot check. 10.1, so on, all these things, there's no spot checks. And what I'm going to encourage you to think of is you've had this experience of doing the homework immediately after it's assigned so that you can ask good questions and get it kind of cemented the next day rather than waiting until just before it's due to crank out all the homework. I'm going to challenge you to do that as a habit. And now that it's not required, do that as a habit for the rest of this class, and to really consider seriously that in future math classes or in any class in general, that if you alter your time sequence so that you're not on deadlines, but you're doing things as soon as they are assigned, so that you can come back the next day and say, instructor, I don't know what you meant by this, and so on. You can really alter your experience as a student. And so that's the challenge from here on out. And if you go to 9.4 book assignment, it says there's a replacement worksheet. And you're only going to be doing these problems, 4, 7, 21, 22, and 54. And if you click on this, it downloads the PDF. And sorry about the quality on this. I didn't like the problems in our textbook, and this is a compilation of different problems from different textbooks, and I copied them with an old-fashioned copy machine and so on, and these were old books too. One of the best books on differential equations I have is a very ancient book, and so I couldn't get electronic copies. I just had to physically copy it. And you have problem 4 and 7, 2 of these tank problems to do. The answers for numbers 1 through 12 are all down here. And then there's 3 more problems, 21, 22, and 52 I got from different books as well. That we've kind of seen some problems similar to these. And when you are, it says answers for 1 through 12 are given at the bottom, so there's extra practice available. Some of these problems, however, lead to differential equations that are not separable, and we don't know how to solve those. The technique for solving those is taught in a differential equations course. So if you are doing ones, besides 4 and 7 in the 1 through 12 for extra practice, if you get to one of those and then, you can't separate the variables, well then just, skip that, because we haven't gone over that yet. But it still could be very good practice even setting those things up though. And so are there any questions?
Can you go over real quick one of the problems from the 9.1 homework?
Okay.
It was number 18.
In 9.3?
What do we, yeah, 9.3, sorry, not 9.1.
Yes. All right, let's go over 18 and 9.3. And this page 618. Okay, so 18. We'll see if it's separable or not. I'm going to power to a power you'd multiply, so that's an alternate way I could write that. I'm going to multiply both sides by dt. Now, I would have to raise both sides if I want to get all the y's to the left. I'd have to raise both sides to the 1 over y power. It's the same as taking the yth root. Now, but the problem is, it would insert a 1 over y. Oops. It would insert a 1 over y on the dt as well. So this would be, and then your dy would be raised to the 1 over y power. And so, yeah, that would not be integratable, and I can't even separate it though. This 1 over y would go to here as well. And then, so it is not separable. And then you don't have to do anymore.
Wait, this is Rowan.
Yeah.
I separated it by doing e to the t times e to the y, plus e to the y.
All right. E to the t times or plus e to the y?
I guess it would be times e to the y.
All right. E to the t times e to the y is e to the t plus y. When the bases are the same, you add the exponents. So that wouldn't recover this.
Fair enough. Okay.
Okay?
Thank you.
You're welcome. All right.
Thank you. I thought it was not separable, but I just wanted to make sure that that was right.
It's good to check. All right.
Thank you.
You're welcome. All right. And if there's more questions on previous stuff, we can get to those in the next class period. And we will stop here. And y'all have a good weekend. I'll see you on Monday.